So, welcome. We were trying to quantitatively derive the change in some thermodynamic quantity when you are trying to produce a two phase mixture. Okay. So, let us look at this diagram which I drew earlier. So, there was this property called X. Okay. So, at some point we are going to say that this property is nothing but the free energy, and the partial molar property, that is, if you take the property curve and if you draw a tangent at some particular composition, then the partial molar property for that composition will be given by the y intercepts. So, that is x1 bar, x2 bar. Later, if this x becomes g, then this becomes nothing but mu 1 or the same as mu a, the chemical potential, and this is going to become mu 2 or mu b at this composition x naught. Okay. So, this is at composition x naught. If I draw another line at some other composition, then that is mu at that composition, mu b. Similarly, this will become mu a at that composition x prime. So, what is it that we are trying to do? We are going to take a large amount of material with the overall composition x naught, and then I am going to produce a small region which has the composition x prime. Okay. So, I am going to take a large amount of material with the overall composition x naught. From there, I am going to take some A atoms and B atoms, and I am going to produce a region which has the composition x prime. What we showed in the previous section of this lecture is that the change in the property associated with this exercise, the delta x, is nothing but property at C prime minus property at C naught, because from C naught we are producing C prime, minus x prime minus x naught times the rate of change of property with respect to composition calculated for the overall composition from which you are trying to produce the material. Okay. So, dx by dx calculated at x naught multiplying the difference in composition, that also has to be subtracted. Why is this delta x not just this, but this? That is because we are dealing with a closed system, and I am trying to take from a material of composition x naught some A and B atoms. If I try to remove, then the free energy changes associated with that is related to these chemical potentials, or the property changes associated with that will be given by these partial molar quantities. So, that I have accounted for and I have derived this expression. Okay. Now, let us proceed a little bit further and let us do a different computation. Let us say that I have this property x and I am trying to calculate this property at the composition C prime. Okay. Now, if I assume that the difference between C prime and C naught, right, it is very small, some delta C. If I assume this, then I know that I can do a Taylor series expansion. Okay. What does the Taylor series expansion give me? It will give me x of C naught plus delta C times x prime at C naught plus 1 by 2 factorial, that is 2 delta C squared x double prime C naught plus and so on. Okay. So, what is this? So, if I want to get the property x at some composition C prime, and if I assume that this property that I am trying to evaluate at a composition which is close to the initial composition that I started with, then I am allowed to do this Taylor series expansion. Okay. So, from this Taylor series expansion, one can see that x C prime minus x of C naught minus del C x prime of C naught is equal to half del C squared x double prime C naught plus. Now, let us recall the expression that we derived in the earlier case. We said that the change in free energy associated with making some quantity with composition C prime from a solution of composition C naught was nothing but x C prime minus x C naught minus x prime minus x naught, okay, dx by dx evaluated at composition x naught. Okay, so, compare these two. So, what is x naught here is C naught here. So, this was at x naught, x prime, x naught, x prime minus x naught. So, whatever x prime and x naught, I have called it as C prime and C naught, and x prime minus x naught, that is nothing but delta C. Okay. So, if you compare these two expressions, you see that the change in the property associated with producing some quantity with composition x prime from a solution of composition x naught is nothing but half del C squared x double prime C plus higher order terms. Okay. Now, if this del C is very small, that higher order terms can be neglected. You can see that to first approximation, the change in property is nothing but half del C squared x double prime C naught. Well, what does that mean? That means the following. Okay, so, I have this quantity delta x, that is equal to half del C squared. So, it does not matter what the sign of del C is. I chose the compositions. So, let us look at this diagram again. I chose this x naught and I chose x prime to the right of this, which means when you take x prime minus x naught, this will be positive. I could have chosen it on this side, okay. For example, some point here, then x prime minus x naught will be negative, but whether it is to the left or to the right does not matter, because this quantity is squared. So, its sign is always going to be positive, and then I have x double prime evaluated at C naught plus higher order terms. So, if I take approximately, okay, let me throw away all the higher order terms, this is nothing but del C squared x double prime at C naught plus some order of del C cube, right. So, there are higher order terms 1 by 3 factorial del C cube x triple prime x naught and so on. So, let me not worry about this order of del C cube terms, because I am going to choose del C so small that del C cube is negligible, del C squared is the only term. Now, you can see that the sign of x double prime C naught decides what the sign of this delta x is going to be. Okay. Let me also now switch, because this is any general thermodynamic property. Let me say that I am looking at the free energy, then the delta G, okay, the free energy change associated with producing from a solution of x naught, right. I am going to produce the solution of x naught, but with small region which has the composition x prime, right. From a solution of x naught, I am going to produce something which is at x naught and a small region with composition x prime. If I try to do that, then this is nothing but half del C squared, okay, which is the change x naught minus x prime squared, and x double prime. So, this in this case will become G double prime evaluated at the composition C naught, evaluated at the composition x naught. Okay. So, this del C also let me call it as delta x, where delta x is defined as x prime minus x naught. So, what does this mean? The change in free energy, the sign is given by the second derivative of the free energy with respect to composition at that point, which is the initial starting alloy. So, if I take this initial starting alloy, if I find out in the free energy versus composition diagram what is the curvature, okay, and that curvature evaluated at this for this system at composition x naught, its sign is going to decide whether this what the sign of this delta G is going to be. Suppose G double prime x naught is less than 0, delta G is going to be less than 0, that means the system is unstable, because by producing this the system can reduce its free energy. So, it is going to spontaneously do that. On the other hand, if G double prime x naught is greater than 0, the delta G is going to be greater than 0. That means the system is going to be metastable, because to produce something like this, the system has to overcome this barrier, right. So much of free energy increase it has to account for. So, this is what we were discussing using the mechanical analogy. What happened in the mechanical analogy? We said that the potential energy curve, for example, this was the mechanical energy. So, we were looking at the potential energy curve and we said that it can have regions like that. So, we said that this is metastable and this is unstable and this is stable, right, this is metastable. So, for small changes the potential energy change is positive, then it is metastable. For small changes the potential energy change is negative, which means it is unstable, because spontaneously it will do that, so that it can reduce its potential energy. In a similar fashion, when this quantity is positive, the system has to overcome the barrier, right. From this metastable state, it is possible for it to go to the stable state. For that, it has to overcome this barrier. Similarly, in this case, unless it overcomes this barrier, the system is not going to be able to reduce its free energy. So, then it will be in metastable state. On the other hand, when this is negative, then the delta G is less than 0. So, it is unstable. As you can see from the geometric interpretation that we gave, okay, so let us go back to this curve, which was the property versus composition curve. You can see that at any composition, if I draw a tangent for all the points which are lying below the tangent, this quantity is going to be negative, right, for all these points wherever, right, this quantity is going to be, for example, here, right, anywhere here, it is going to be negative, which means the free energy change is going to be negative. That means spontaneously the system will undergo the transformation. On the other hand, for all the points which are above this line that we have drawn, the change, because from here to here, is going to be positive. That means the system is going to be metastable with respect to those changes. Okay. So, we are going to stop at this point. So, we have related the free energy change associated with infinitesimal fluctuations, and we have derived it for a general case where we did not make any approximation. Then we compared it with some infinitesimal fluctuations, so that you can do a Taylor series expansion and you compare the two expressions and you see that the change in the property, in this case the free energy, associated with producing this two phase mixture from a solution of a given composition, where the second phase has a particular composition, can be related to the second derivative of the free energy with respect to composition, and that quantity is known as the curvature of the free energy versus composition curve. So, the curvature sign basically decides what is the free energy change. What happens when this curvature is 0? The free energy change associated with this is 0. Okay. So, it does not have a tendency either to go this way or that way. So, it will be stuck there. So, that is the point that we drew as the spinodal line in the phase diagram. That is why it is the line that separates metastable regions from stable regions. So, spinodal line basically tells you that if you are inside the spinodal region, if you produce a two phase mixture, that will spontaneously happen because the free energy reduces automatically. Outside of it, if you try to produce a two phase mixture, then you have to overcome a barrier before you can produce a two phase mixture. So, the system is metastable. Overcoming that barrier is through nucleation. So, outside the spinodal, the mechanism of two phase formation is by nucleation followed by growth, and growth is controlled by or described by the Fick's laws, right. Growth is described by the diffusion equation. On the other hand, inside the spinodal region, you have skipped this first step. It does not have to overcome any barrier. So, there is no question of nucleation. Everything is simply given by the diffusion equation. Everything is like growth in the other case. So, we are just looking at how the system is going to undergo this transformation from a single homogeneous phase to two phase mixture. The reason it happens spontaneously is because the free energy change is negative, and that is what we have derived and shown. Okay. So, in the next section of this lecture, we will take a look at our regular solution free energy and see what that means. Thank you.